So having seen higher Fréchet derivatives in the previous video, we'll now make sense of the Taylor series expansion for Fréchet differentiable functions, or k times Fréchet differentiable functions. So in particular, we're going to give sense to these expressions that we have in one-dimensional calculus, where f in the neighborhood of x naught is expressed in a polynomial. Well, the constant term is f of x naught, then we had the other terms of derivatives, and we have a remainder that's little of h to the k, meaning if you divide this by norm of h to the k, it goes to 0. So how do we understand this? So in particular, notice that this symbol here doesn't really make sense, but we're going to see how to make sense of it. Well, I mean, it's just a shorthand, if you want to know, for age, written j times, which is an element of vk, vj. So what's the precise image? Precise image is just what I said. Well, you define age superscript j, h to the j, like just an element of v to the j, which is h j times. And now if your f is a function between Banach spaces v and w, defined over an open set, k minus 1 times differentiable over the whole of u, and with a kth derivative at x naught. So if all those things hold, then you have your Taylor series expansion. It just means, well, f of x naught plus h for small h is this polynomial. Well, polynomial just because it's a sum of j linear functions from j equals 1 to k. So it's the polynomial plus a remainder term, which is just saying, well, the difference between a and b. What we're saying is that a minus b, the norm of that, when you divide by the norm of h to the k, that goes to 0 when h goes to 0. So it's really the same thing as in one dimension. The proof is going to be, of course, more complicated, but the intuition is still the same. So how does it go? Well, we're going to prove something that may look stronger, which is that, well, okay, first of all, let me note that if you look at this for k equals 1, then say k minus 1 times differentiable, that's just saying it's saying nothing. And saying the Fréchet derivative order 1 exists, then we have this just by virtue of the definition of the Fréchet derivative. Okay, for k equals 1, this is a definition of Fréchet derivative. So if f is Fréchet differentiable at x naught, we have this formula for k equals 1 again. So that case is covered, and we can do an induction, and with the basis k equals 1. And in the induction, it will be convenient to prove this slightly stronger statement, which you can also get for k equals 1, just from the definition. I mean, it's basically rewriting the definition, and you get this, right? So what's stronger? We're fixing an epsilon, taking a super of h with norm less than epsilon, and x naught plus h and u. And when we do that, and then we take epsilon going to 0, when we show that this goes to 0. And we assume that this limit exists as a 0 for k minus 1, and any function f that's k minus 1 that times differentiable. Okay? Well, okay, maybe you need to think a little bit about this, but it's really the same thing. So we're going to prove this stronger, seemingly stronger form, which is really the same. So how do we do this? So as in many other points in our life, we're going to use the mean value inequality. It's one of our tools for bounding things in terms of the derivatives, right? So, okay, how exactly are we going to do this? Okay, first of all, technicalities. Let me say that I have x naught here. This is u. I fix a radius to make sure that the whole ball, okay, that doesn't look like it's inside u. Let me have to fix this. I have the ball, and now I have u. I fix a radius to make sure that this whole ball is contained inside u. So if I take h of norm less than h, I have this. In particular, I'm going to look at the sup only for h less than or equal to epsilon, which is less than r, to make sure that when I look at x dot plus h, that's contained in u, and to make sure that I can compute everything. So now let me stick with one such h, and I want to bound this difference. I'm going to do that by taking derivatives. So of what function? Well, in principle, I could differentiate everything here. In terms of Fréchet derivatives, it is slightly more convenient to say that since I have these properties, I know that age is in, right, that the whole line segment between x naught and x naught plus age is contained in the ball, which contained in u, and I can apply the mean value inequality for a curve, right, which is a curve that maps t to f of x naught plus ch minus f of x naught minus this. Okay, at t equals 1, it gives me what's above. At t equals 0, it gives me 0. You just have to check it. Okay, so let's then compute the derivative, right? And now things start looking a bit funny and similar to what we expect, right? So take a t and differentiate this guy. So this, of course, has 0 derivative. What about this one? We can use the chain rule, and this is what we get. Derivative of f applied to h. Now we have these guys here. I mean, they're like t to the j times a term that does not depend on j. So just differentiate the scalar. Of course, when we do that, we get t to the j divided by j factorial. The derivative of that is t to the j minus 1 divided by j minus 1 factorial. And now we have the derivative of f, which we know is k minus 1 times differentiable. So I want to see the Taylor series for df here. I want to find it here so that I can apply the induction hypothesis. How do I do that? Okay, let me say that h of t, h sub t is t times h, and then I can write this like this. What about this polynomial here? Well, notice that I have h to the j, I have a j linear transformation, I have t to the j minus 1. So I just move these factors all inside, and I'm going to get something like th of th, j minus 1 times, and then a final h, right? So I have j minus 1 factor is equal to t, which comes to these guys, and then h. And of course, th is h sub t. So this is what I have. And now, once again, my isomorphisms come to the rescue, right? So what's the first one of these terms? Well, it's just df, right? J equals 1 gives me df x naught. J minus 1 factorial is 1. H to the j minus 1 is nothing, so j equals 1 in this case. I have this guy. What about the other ones? The other ones are like djf of x naught. Let me write it again. ht, h. We do the same trick that we did in the previous proof. This is a j linear transformation. I want to look at a j minus 1 linear transformation that takes ht j minus 1 as input, and outputs a linear transformation that takes g as an input. So now the magic that I have accomplished is that, well, this is a linear operator applied to age. These are all linear operators applied to age. These guys, including this, right? So this is a linear operator for v to w applied to age. And of course, here also have a linear operator, this guy, applied to age. So I'm just going to factor this age out. If I look at what I have, look, isn't this the Taylor series for df, but up to order k minus 1, right? So this whole thing here, sorry. Forget about this age for the time being. So I have df of x naught, just a value of the function x naught. Then I have the first derivative of df applied to h sub t. Then I have the second derivative applied to h sub t squared. A third derivative applied to h sub t cubed. And dividing by the right factorial will go all the way up to the k minus 1th derivative of df. So this is what I have. So if I write, when I write Taylor of order k minus 1, it's just this polynomial made up of derivatives. What I have is that I have this derivative, for sure derivative applied to age. And then I have the Taylor series of the derivative up to order k minus 1 applied to the same age. Here I'm strongly using the isomorphisms. Now this is really wonderful because when I compute this, and remember, all that's inside these brackets here are linear operators. So if when I compute the norm of this linear operator applied to j, I can bound it by the norm of the linear operator, which is here, df minus its Taylor expansion, and I multiply by the norm of age. Right? That's just the definition of the operator norm. What's the conclusion? We wrote this difference between f of x naught plus h minus the Taylor series as gamma 1 minus gamma 0 for a certain curve gamma. By the mean value inequality, we get a bound on this thing just by an unbounded derivative. And if we look at it, so the bound is something like is the soup of what's in here. But notice here I was dividing by h to the k, and I get this factor of h coming from this calculation. So I'm going to end up with h to the k minus 1, and this supremum. I don't quite have h here, I have h sub t, but I have a supremum over t in 0, 1, which I get from the mean value inequality. So, okay, what's my assumption? My assumption is that all functions satisfy the Taylor series expansion up to order k minus 1. So I know that this guy goes to 0 when divided by h of k minus 1. Or almost, right? Because here I don't have h, I have h sub t. But h sub t has norm less than that of h. So the whole expression, right, this is what I want to bound, this is what I get. It's, well, okay, it should be more clear here about what I mean. This is x naught h tilde. I can just say, well, I'm looking at the function df computed x naught plus h, but it's h sub t, doesn't matter, minus the Taylor expansion. And I know that if I divide that by the norm of h sub t, and I take a soup, that goes to 0. That's what I'm doing over here. So my h here is playing the role of ht, but I'm giving more freedom, choosing any h tilde less than epsilon norm. So in the end, I reduced this estimate for the Taylor series of order k of f to the Taylor series of order k minus 1 of df. If f is k times differentiable, then df is k minus 1 times differentiable, meaning that this second guy goes to 0 when epsilon goes to 0 by the induction hypothesis. And that means I'm done because I prove it. This goes to 0, this must also go to 0. Now, I'm going to finish with the theorem I'm not going to prove. I'm going to, on purpose, leave it as an exercise I want you to try and do. It's not an easy exercise, but we're going to go through it in class. Okay? But you can assume this exercise is true, and that will make your life easier. The exercise is as follows. So, assume you have f. You don't know whether it's differentiable or not, but you know it has something like a Taylor series expansion, meaning, sorry, there's a k missing. There are a bunch you can associate to each point of view. J linear operator from V to W for j equals 1 to k. These J linear operators depend continuously on the point of view that you pick. And you know that if you look at fx naught plus h minus f of x naught, you subtract this polynomial here, divide by the norm of h raised to k. This whole thing goes to 0 when h goes to 0. Of course, if I have the Taylor series, Taylor polynomial here, this is going to work, but I don't know yet that that's differentiable. So the magic of this theorem is saying that if I have this Taylor series expansion here, or this Taylor series like expansion, and if I know that these guys are continuous, then it must be that these guys give me the derivatives back. So it's not only that it's not only that I find derivatives, but I also discover at this point that f is differentiable. Remember, don't assume that. So once you have this exercise, you can use it like, one thing that you can do is write all the partial derivatives of this inverse function applied to h, k, where inverse maps invertible linear operators invertible to their inverses. So that's one exercise that's going to be in your assignment. You could do this example by hand, but it's not the easiest way to do it. Well, we computed the second derivative by hand, but now we know a way, just by looking at these power series expansions we had before, we know a way to actually differentiate this map that does not require going back to the definition every single time. And of course, There are many other things you can do with Taylor series. We're going to look at some examples from our D to R in the exercises where the Taylor series gives you local information about the function, but that comes later. For now, I'm done, and thank you.